So yesterday we almost finished the calculation of the Fermi level for metals. Just to remind you, so the Fermi level, Fermi energy for metals, we have calculated. Please, this is for metals. Okay, we calculated that it is equal to h squared over 2 times m, and then 3m over 8 pi 2/3, with n is the free, or Ne, what used to, so the density of free electrons, and obviously it is given per cubic meters per volume. Yes, and then we said that if we have the density of state, the density of free electrons, sorry, we can calculate the Fermi level, and vice versa. If we have the Fermi level, we can calculate the density of free electrons. Also, I insist that so if you do this calculation like that, the value that you will be getting will be in Joule. And usually the Fermi level is given, or the Fermi energy is given in electron volt. So you have to convert to electron volt. Okay. So one question. So yesterday, what we did, we calculated the let's say the energy, the Fermi level for the aluminum, and let's say if we so let's say if I give you what is the Fermi level. No, if I have the Fermi level of a metal that is equal to 5 electron volt, so one question would be, for example, so what will be the speed of the electrons at the Fermi level, at EF level? Okay, any idea? Hello, any idea? Are you following? So if I am giving you, okay, the electrons are at the Fermi level of 5 electron volt, what will be the speed of the electrons at this Fermi level? So any hint, any idea? Okay, can you hear me? Okay, how did you get it, Reem? So I have one question. You are giving me a speed that exceeds the speed of light. Yeah, yes, you're right. The kinetic energy is equal to 5 electron volt. Okay, yes. You say that the kinetic energy, 1/2 mv squared, is equal to 5 electron volt, right? Yeah. But then you obtained a speed that is 1.32 10 to the power of 10 meters per second. Well, we have seen in physics 222 that the speed of light is this. Well, this is bigger than the speed of light. It's impossible. So what will be the mistake? Yes, this is correct. But what is the mistake here? So we want to calculate the speed of those electrons. What is the mistake? Now, 5 electron volt is a low energy, so definitely the electrons will not have a relativistic speed. So which means we can still use classical equation of kinetic energy, which is 1/2 mv squared. So there is no relativistic phenomena here. But what is the mistake in your opinion? In physics 1, when you calculated 1/2 mv squared, the kinetic energy, what was the unit? When you use this in kilogram and the speed in meters per second, what is the unit of the energy that you get? Hello? Hmm. Well, I don't see anyone answering. It's a very easy question. In physics 1, when we calculated the kinetic energy of a particle, let's say I have a particle that has a given mass in kilogram, a given velocity in meters per second, and I'm asking you to calculate its energy. What is the unit of the energy? Can you hear me? Okay. Hilal, can you hear me?
Yes, I can hear you, Doctor.
Okay. Jasim, can you hear me?
Yes.
Reem,
Yes, Professor.
Omer. Okay, Omer has not been answering since the morning. Okay. Oh, now, what is the unit of energy? Come on. In Joule. So the unit of the energy, when you use this in kilogram, this in meters per second, it's in Joule. But here, the Fermi level is given in 5 electron volt, in electron volt. Okay. So what should we do first? Before getting the speed, what should we get? What should we do? Yeah, so we need to convert 5 electron volt to joule. And 5 electron volt to joule, of course, will be 5 times 1.6 10 to the minus 19, and this will be joule. Okay. Okay, so now let's do the calculation. So now 1/2 mv squared is equal to the Fermi level. Of course, I will convert it to joule. This means that the speed will be equal to 2 times the Fermi level divided by the mass of the electron, everything squared. Okay. Now the speed, so the Fermi level is 5. We need to convert it to joule, minus 19. And then the mass of the electron is minus 31. Okay. Well, if you do this, it's now you can understand why you get or you got a very high speed. Here you get the velocity is 1.3 10 to the power of 6 meters per second. Okay. Okay. Is this clear, please? So you can see that it's more than 100 times smaller than the speed of light. Okay. Any questions? So those are the type of questions that you can have. Okay, so then let's continue. As I mentioned, we also calculated the specific heat of solids, and the specific heat is given by derivative of the energy, the total energy with respect to the temperature. And we mentioned that the quantum mechanics in the density of state it gives the total energy can be calculated as the integral of over all state, the state density or density of state times the probability of occupation of each state, and then the energy. And then this is, as I mentioned yesterday, this is the energy, the total energy, or the equation of the total energy. Okay. Now, and as I mentioned, quantum mechanics could give us a very good explanation, because if you do this, you will see that the specific heat capacity, specific heat of the metal is equal to pi squared over 2, a constant k squared divided by the Fermi energy times T, and you can see this is a constant, and it is proportional to the temperature, which is exactly what we see in experimental observations or experimental measurement. Okay. So, by the way, this is a lengthy calculation. It's not included in this course, but I just want to give you this formula so that you know that unlike classical physics that gives you a constant specific heat regardless of the temperature, which contradicts the experimental measurement, no, the quantum mechanics calculation gives us the good agreement with the experimental observation. Okay. Okay. Okay, so let's go to something very interesting. By the way, in this course, and I wanted to emphasize this also. So in this course, this is just between brackets. In this course, we will be talking. We have talked already about metals, and we will talk about semiconductors. Of course, we will also talk about superconductors and other materials, but those are the most actually relevant ones. Now, in electrical engineering, most of the time you are faced with connections between metal. I mean, contact between metal. You are building a device, an antenna or whatever, and then you have you are doing a metal, for example, aluminum, copper. You will be faced with the metal semiconductor contact. Okay, and you will be faced also with semiconductor contact. You will take a semiconductor and then you will put it in contact with another semiconductor. This is what we will be doing in this course also. We'll be covering, okay, if you put two metals together, what happens? So because we have already seen the metals, now we will talk about metal contact. Metal contact. So when you put two metals, and we will give the example of two metals that are platinum. The platinum has a work function of 5.36 electron volt, and molybdenum has a work function of 4.20 electron volt. This is 4. Remember, what did we say about any metal? A metal has the following. It has a Fermi level, let's say at a very, very low temperature, Fermi level. All the states are occupied here. And then this is an empty, but not forbidden, an empty state. And this is the outside. Okay? And this is the work function. The work function is the energy required to get an electron extracted from the metal outside. Okay, this is what we have seen in the photoelectric effect. Now let's see what you put, what will happen if you put these two metals, which have, this is the most important thing, these two metals, they have different work function. If you put them together, let's say I will write it in a very, so this is platinum, and this is molybdenum. Now, you can see that in platinum, the work function or the Fermi level is lower, because the work function here is 5.36 electron volts. So the Fermi level is lower In the case of molybdenum, the work function is smaller. This is a work function, 4.20 electron volt. And this is the Fermi level. So what happens is that if you put them in contact, if you approach them, those electrons that are at higher levels, they want to migrate and they will tunnel and they will go to the lower energy values of EF, okay? Because they want to go to the lower energy state. Because this is an empty state. This is an empty region. So the electrons will easily tunnel through and get here. So what is the result? The result is that we will have the two metals, okay? Let's say this is, and they will have, so those electrons will start moving from molybdenum to platinum at a certain moment, and then the Fermi level start getting increased for this. At a certain moment, the Fermi levels, they will align, they will reach the same value, okay? They will reach the same value, and then there will be a kind of an excess of energy that we call contact voltage. A contact voltage will appear, and this contact voltage or energy is equal, so the contact voltage, I will call it Vc, is equal just to the work function of platinum minus the work function of molybdenum. Okay, so you will see that if there is a potential difference that is created between these two metals, just because you put two metals with different potential difference. Work function. Different work functions. This will create the electrons from one that has the smallest work function. They will tunnel through and go to the other one, and they start to elevating or raising the Fermi level of the other one until both Fermi levels remain the same, reach the same level. This means that since the electrons now are at the same level, they don't have any preference. They stay where they are, and then there will be, because of this difference, those electrons that are jumping from here to here, they will create a difference of potential or energy, and this energy is just the difference between the potential, the work function. Of course, if you want to calculate the potential difference that is created, or the contact voltage, this is called the contact voltage. Now, there are also some, in some textbook, they also call them built-in voltage or built-in potential. I prefer the contact voltage because for the built-in, we will see it in later in the semiconductors, in p-n junction. So the contact voltage will be calculated as the work function of one metal divided by the electric charge. Now, in this case, we can easily calculate it. So the energy is equal to what is equal to, so the work function of molybdenum is 5.36 electron volt minus 4.20 electron volt, and this energy will be 1.6 electron volt, which means the contact voltage in this case between these two metals is 1.6 volt. Okay. Any question? Any question? Okay.
Professor, is it 1.6 or 1.16?
Probably. Well, yeah, maybe. Let me do the. Yeah, maybe you are right. I just no. Let me see the value of the work function. Yes, it's 1.1. Sorry, I don't know why I made. Yes, okay. So there is a mistake here. Let me see. Yeah, yes. There is 6 here, and you are right. It's 1.16. Yes. Yeah, all right. So I should correct it in my note. Okay. Any question? If not, I will start the. So let's get just. Can I get just 2 minute pause, please, and then I will resume. I will just pause. In fact, the reason I made a pause is I just wanted to upload this part. So we are done with chapter 6. Chapter 6 we cover the metals, the Fermi level, the density of states, etc. Now we will go to the what we call the band theory of solids. The band theory of solids is the one that explains to us the metal behavior, but most specifically the semiconductors behavior. Okay, this chapter, most of the time, I give it for as an information chapter. I don't ask a lot of questions from this chapter. So let's see explain a little bit now. So what is specific with solid and semiconductors? In fact, in semiconductors, the potential of semiconductors is periodic. You can see it here. It's periodic. Well, because let's say in crystals, for example. So let's say in crystals, you have a regular structure. For example, you have atoms at regular structures. Okay, and again, if you do again another, so you have atoms at very regular structures, which means the potential to which the electron is subject is periodic. So it's the same pattern, and that's why it's represented here. For example, in some cases, you can see that the potential is a certain value from, let's say, from 0 to A, it is 0, but from A to A plus B, it's V0, and so on. So it's a periodic potential. Periodic potential, what do we need then when we have a potential? We use this potential to write the Schrödinger's equations. We solve the Schrödinger's equation. We get the wave function. The wave function gives us the probability density function, and the probability density function gives us or helps us determine the energy levels, the anything about the electrons, the radius of the orbit, and so on. So this is what we do. We will not cover it in detail because this is not the goal of this course. Just to give you the difference between a metal and a crystal like that has a regular structure. So this is how we do the solution of the Schrödinger's equation. So we do several things. Now, what is very important is when we put the boundary conditions. Remember, when we solve Schrödinger's equation, we get the wave function. We start looking at the boundary conditions. The different boundary conditions means the wave function must be continuous. Okay, if you have a potential, let's say if you have a region, this is region 1, and this is region 2, and this is region 3. So the wave function 1 at this specific point, let's say A, must be equal to the wave function 2 at A. So we start looking at those boundary conditions. Now, in the case of this periodic potential, what is very interesting is when we look at the boundary conditions, those boundary conditions gives us something very interesting. It gives us some areas that are forbidden, bands. For example, you can see here the arrow, the red arrow, tells us that this region is a region where we can find the electron, or at least where the electron can be located or can occupy. So these regions, the electrons can occupy. Well, why? Because these regions, they are between -1, +1, just because of this cosine. Because cosine cannot be more than 1 or less than -1. Okay, so you can see that just by writing the Schrödinger's equation, solving it, and studying the boundary, applying the boundary conditions, we see that the electron can only occupy certain band, not only one point, a band. And there are other bands that are forbidden. Those ones. Those ones are forbidden. Okay. And you can see that we have an allowed region, yes, and we have a non-allowed region, non-allowed region, non-allowed region, and then allowed, allowed. So this means it's like if we have a band, and you can see it here also in this plot. So this is a region that is allowed, so band, and then nothing, then band, then band, then band. This is exactly what you see in a semiconductor that we have seen in physics 2, that a semiconductor, we'll see it in detail, but this came exactly from this Schrödinger's equation solution for periodic potentials. So the semiconductor, we have seen that it has a valence band. We'll talk in details about it. This valence band, the electrons are there and the holes also. However, unlike the metals, this is forbidden. Forbidden. And then this is a conduction band. This is fully packed. If the electron want to jump, if you want to make it conductor, the electron must jump. They cannot be here. There is nothing to be here. And this is because this non-allowed region is this one, correspond to those bands. And that was one of the success of Schrödinger's equations and quantum mechanics that explains to us the behavior of semiconductors, thanks to this band theory of solids. Okay, I will not go into details. I just want to okay, so this is all what I wanted to you to know. There is another thing important, is the effective mass, and here I will cover it in detail. Effective mass. Another success of quantum mechanics is what we call the effective mass. Now, the mass of the electron, we know that the mass of the electron is equal to 9.1 10 to the minus 31 kilograms. However, experimental measurement showed that this is the mass of the free electron, let's say in a metal. Experimental observations showed that the effective mass of an electron in a solid differs completely from the conventional value. So the mass of an electron in a solid is different than the mass conventional one. Okay. Now, why? Just because in a solid we are treating, when we treat, and in fact we could not understand this. Why? Experimental measurements. Those are experimental measurements. Tells us that the mass that we get for an electron is different than the conventional mass that we know. And in fact, we could not understand this until we applied quantum mechanics. Quantum mechanics. Which means until we treated the electron as a wave. When we treated the electron as a wave, we could understand this. Now let's treat the electron as a wave. Let's do this calculation. So we know, now who can tell me when the electron is treated as a wave packet, we have the phase velocity and the group velocity. Which one of them gives us the velocity of the electron or the particle? Which velocity gives us the velocity of the electron, of the particle, when we treat the particle as a wave? Hello? No, it's the group velocity. Remember, velocity of the particle. Remember, when we did the phase velocity, we said that the phase velocity is the velocity of the particle divided by 2. We did the calculation. So the group velocity is the one that gives us the velocity of the particle. Now, what is the group velocity? Can someone give me the equation of the velocity, the group velocity? So the group velocity is the derivative of the angular frequency of the wave with respect to the wave number, right? Now, we know that the energy of the wave or the particle is equal to h bar omega. So this, I can use it. So the group velocity. So by the way, sometimes I mention group velocity like that, sometimes a group velocity with gr. So the same. So the group velocity is 1 over h bar and then dE over dk. Okay. Now, when the electron is in a solid, so it is subject to a force, and the total force is equal to ma, mass times the acceleration. Okay. Well, the acceleration of the electron is the derivative of the rate of change of the group velocity, because the group velocity gives us the energy, the velocity of the particle, which means I can replace here is 1 over h bar, right? The derivative of this, which I can write as 1 h bar, the derivative k, okay, with respect to yeah, respect to dt, right? And then dt with respect to dk, and then the energy with respect to dt. Okay. Now, in fact, what I can do is, what did I do here? I think, no, sorry, this is not. So the derivative with respect to, let me just make it everything and so make it clear. So the derivative of dt, I can do, it's the derivative of dk with respect to dt, and then d over dk. Okay? This I can do. So then I replace. So I replace here. So the acceleration of the particle is equal to 1 h bar, and then the derivative k dt, and then d over dk and dE over dk. This is just the second derivative of the energy with respect to k squared. Okay, the second derivative. And then, so A is equal to 1 over h bar, the second derivative of the energy with respect to the wave number, and then dk over dt. Are you following? Okay. Now I know that the wave, the momentum is equal to h bar k, which means k is equal to p over h bar. So, which means that dk is equal to dp over h bar. So I replace dk by its value here. This gives me the acceleration is equal to 1 over h bar, the second derivative of the energy, and then dp over dt with 1 over h bar. No, sorry, h bar. This is h bar. This is h bar. Okay, which gives me 1 over h bar squared, d squared e over dk squared, and then dp over dt. Okay. So the acceleration is equal to 1 over h bar squared, d squared over, and then dp over dt. Well, then the rate of change of the momentum is equal to the acceleration times 1 over, or, no, instead of doing this, times 1 over h bar squared, d squared over dk squared, and everything minus 1. What is this? Well, this is the mass. This is the mass of the electron, just F equal ma. Okay, this is just F equal ma. So this means that the effective mass of the electron, is given by, so usually we put a star on it, is equal to h bar squared, and then the second derivative of dk squared, 1 over h bar squared minus 1. By the way, I think there is a, let me just correct a mistake here. So, yes, just, I think, just repeat here. So here, so we have the acceleration 1 over h bar squared, and then d squared over dk squared, and then the momentum, sorry. This is, what is this? This is, what is dp over dt? I think I did a mistake here. I will get rid of everything, and so there is a mistake here. Just forget it. I hope you are following. It's a very, very minor mistake. So we started, we reached this point, this one. Okay, we reached this point. Now, the acceleration is equal to 1 over h bar squared, d squared e over dk squared, and then dp over dt. This is the equation. Okay, can you tell me what is dp over dt? dp over dt, what is p? P is the momentum, is dmv over dt, is mdv over dt. What is this? Any idea? Hello? This is just m times the acceleration. So this means that this is the force. This is just the second law of Newton. The second derivative, the derivative of the momentum with respect to time is equal to the derivative of mv, which is ma. So this is just the force, which means this is the force. So in other words, the acceleration is equal to h bar squared d squared e over dk squared, okay, and then times the force, right? This means that this is 1 over m, because a is equal to f over m. So this quantity is 1 over m. So 1 over m is equal to 1 over h bar squared d squared e over dk squared. Well, this means that the effective mass, in fact, now is equal to h bar squared and then d over dk squared to the minus 1. This is the effective mass of the electron. So Usually the effective mass is different than the mass of the electron, depending on the solid. You will see sometimes, for example, in examples 0.6 ME, sometimes it will be 0.8 ME, sometimes it will just be equal. So it's different. So, yeah. Okay. Any question? Is this clear? So the effective mass, now in many questions, we will ask, for example, I will ask you, okay, in a solid, there is whatever, take effective mass 0.8, the mass of the electron. For example, if I ask you, take the ME, the effective mass is 0.8 ME. This means it's just the effective mass. You will just multiply by 1.6 10 to the minus, no, sorry, it's not 1.6, 9.1 10 to the minus 31 kilogram. Okay, this is a new effective mass. Now let's look at the at one example. Again, one example. We have seen why the effective mass, why the effective mass of the electron is different than the mass of the free electron. As I mentioned, because if the electron is inside a solid, like semiconductor, it is subject to a potential. Okay, and this potential change the mass. Okay, change the mass, affect the mass, the observed mass. We are talking about the experimental observation. However, if the electron is free, we should have the effective mass equal to the mass of the electron. Now, we have seen in chapter 6 the theory of free electron of metals. So in a metal, we have seen that the energy is equal to h bar squared k squared over 2m. Okay, k is the wave number, right? We have seen this. Okay, if you remember, we have seen that k squared, when we solve Schrödinger's equation, is equal to 2me h bar squared. Okay, why? Because the electron is free. If you remember, the electron was in an infinite well, and here the potential is 0. So when you write the Schrödinger's equation here, it will be minus h bar squared over 2m. The second derivative of x is equal to e psi, and which will give you d squared psi over dx squared plus 2m e over h bar squared psi is equal to 0. And this is k squared. This is exactly this one, because the electron is free. Okay, so if the electron is free, let's see if we apply the rule of the effective mass. So we know that the energy of the electron in a free electron is like this. Now let's calculate its effective mass. By the way, this is the mass at rest, okay, because the electron is free. Now we know that the effective mass is equal to h bar squared, the second derivative of E with respect to the wave number to the power of -1. Now let's apply this to this. The first thing I need to calculate is the second derivative with respect to k squared, which is the second derivative of what? The second derivative of this one. So of h bar squared k squared over 2m. Okay, this is a constant. So the second derivative of this is 2, because the second derivative of k squared with respect to k squared is the first derivative is 2, and then 2 dk over dk is 2. Okay, so this will give me 2 times h bar squared over 2m, which is 2, which is h bar squared over m. Okay, right? Now I replace in the effective mass. So the effective mass is h bar squared 1 over this one, which means m over h bar squared. I simplify and I prove that the effective mass is equal to the rest mass or the mass of the free electron. This is because this electron is free. It is in a metal, the theory of free electrons in the metals. Any questions? Any questions? So I will stop here. Now, as I mentioned, what will, let me stop recording first. The information that I will say now, I will give it in an email.